Hello everybody and welcome to this module. So basically from this module, which is the second module, we discuss the kinematic of a continuum. This is the place where we start to discuss the originate of strain, the mathematical modeling, and also different types of strain tensors like the infinitesimal or small strains like the Cauchy strain tensor, as well as the Green-Lagrange strain tensor, which is for the large deformations. We will discuss about this later, but all in all, the point of this module or chapter is all about the deformation and strain. So let's get started. We start by reference and current configuration in this video. And then we explain the Lagrangian and Eulerian point of view. And then we end up with the material derivative. All right. So let's get started by reference and current configuration. Suppose you have a coordinate system like the one you see here. So we have some capital letters X and the other is small x. So suppose you have a configuration like the one you see in here, and this is a continuum. Why? Because if you select a particle right over here, then you have infinite number of particles around it. So we can call it a continuum. And we are discussing this kind of continuum. We have also some other types of continuum, which are not covered in this course, but, in this topic in solid mechanics, but we are specifically talking about this kind of, continuum where every particle is covered by infinite number of particles. So if you have a particle right over here, say here, you can characterize its position by a vector like capital X. And if after time t, this particle is right over here, you can characterize its position by a vector like small x. So basically this is your particle at time t0, for example, and this is your particle at time t. This is the same as we had before. So we have like x like 1 and 2, and you had a particle right over here on this on this path. So we used r of which was basically a vector. So we can characterize its position by a vector r, and this r is basically a function of t. This is the same. For example, this particle, we use another r. So maybe r, this is r1, we use r2t. This particle, we use r3t. So since we have infinite number of particles, therefore we won't be able to write to just draw a kind of line here and say okay, this is the vector r and t. This is somehow completely absurd and also mathematically impossible. Therefore we say that we have this configuration here where we call it a reference or the base configuration. And we say that this particle right over here is basically changed to this particle, changed to this configuration, and this is the same particle, but it is at different time here in the current configuration. Therefore, we will be able to characterize each point at the reference configuration as well as the current configuration. So we write it like small x. So this is the current position. This is a function of capital X and t. So we say that this particle, x, is a vector, for example, that is a function of capital X, the initial, and t, the initial configuration, or the initial point, or reference point, and t time, where, or as the book is stated, with basically x, small x, equal to x, capital X at t0, where we say that, okay, this is basically the same as capital X, because here at t equal to 0, or at the reference configuration, we have small x actually coincides with capital X. So that's why we use capital X in here. So at time t equal to t0, or at initial time, the reference configuration and current configuration are the same. So for example, if you have a configuration like here, and this is the reference configuration, and you have this is the same particle, and the red one, the red dash, actually is the current configuration. It says that both x and x are the same at t0, at the reference, at time equal to, at the initial time, sorry, both initial and current configuration, they coincide. So they are the same. That's why we wrote it like this. So you put an angle around it. Great. So that means if you have, for example, x1 is a function of x1, x2, and x3 and time. So at the current configuration, x1 is a function of all the elements of capital X, or the initial configuration, at time t, where x1 at the initial configuration is a function of x1, x2, and x3 at time equal to at the initial time. This is the same for x2, where we write x2 is a function of capital X1, x2, and x3 at time t, where the initial x2 is basically a function of capital X1, x2, and x3 at t at the initial time, and this is the same for x3. So we have x3 at the current configuration, a function of capital X1, x2, and x3 at time t, where x3 is a function of x1, x2, and x3, all capital, at the initial time. So basically, we call these the material coordinate, or base or reference coordinate, and we call this motion of continuum. Or current configuration. So let's clear this out. So suppose you have a kind of initial condition like this. So you have x1, x1, x2, x2, x3, x3. And this is your initial, or let's say, reference configuration. And due to some loading, for example, or due to some deformation, basically this is changed to, I don't know, maybe oops. Something like this. So you say that your initial configuration, for example, for this node here, which was x, is now here. This is a small x. So the initial configuration is x at this point of this particle, for example, and this particle is here, and this is small x, and this is the current configuration. So we can characterize this configuration, the current configuration, using the previous one and the time t. So after time, let's say t, this happened. So this was, for example, at time equal to 0, and this is after time t. For the initial configuration itself is a function of, the position of its first position. So its positions like this. So it has an x1, x2, and x3 coordinate. So this is the initial, and time 0 at time equal to, at t, for example, equal to t0 or t equal to 0. This is all about this, this whole picture, or this is a schematic. Okay, let's get rid of this, and let's clear this even with an example. So here I have an example 311 of the book, where it says that you have a cube like this with unit sides. So this is A, B, C, and D, and all of these are 1, right? So it says that this is the current, this is x1 and this is x2. So you have this as the reference configuration. And basically you have a motion like x is equal to capital X plus kt x2 e1, where this one is basically bold, so it indicates that this is basically a vector. So you have x1, x2, and x3. So I will write it with another color. So this is x1 e1 plus x2 e2 plus x3 e3 plus kt x2 e1. So we have this motion here, and this is of course a vector as well. As it said, x is equal to x1 e1 plus, maybe write it like this, x2 e2 plus x3 e3. 3. So if this square here, it undergoes this deformation or this motion, how it is changed. So we have, for example, 4 particles here. We have particle A, B, C, and D. So if we can calculate how they are deformed after, after time t, for example, so we will be able to know what is the current configuration. So since we have this motion here, which is equal to this, we will be able to write 0, 0, 0 as the coordinate of A. So if we plug the coordinate of A, we will be able to get x equal to, so this is all 0, 0, 0, plus, and this is also 0, because we are in the initial coordinate. So this is x1, x2, and x3. All of them are 0. So if I write it like this is the star. So if we plug into a star, so x is equal to, this is 0, 0, 0, and this is also 0. So what we get is 0 E1 plus 0 E2 plus 0 E3. So basically, A remains at its position. We next move to B. So B has a coordinate of 1, 0, and 0. So if we plug it into this star or asterisk coordinate, so it is x1, x2, x3, then under this, let's say motion, so x1 is 1, and this one is 0, so it becomes 1 plus x2 is 0, so 1 E1 plus 0 E2 plus 0 E3. Then we have point C, where the coordinate is 1, 1, 0. This is x1, x2, and x3. So x is equal to, so x1 is 1, so we have 1 E1, 1 E1 plus 1 E2 plus x3 is 0, so 0 E3 plus kt, and x1 is also 1, so it is 1 here. So it is 1 plus k, sorry, it is 1 plus kt E1 plus 1 E2 plus 0 E3. So this one remains here, this one remains here, but this one is basically has the same, let's say, x2 coordinate, but here we have an increase assuming that k is larger than 0. So since time is also greater than 0, so we have a positive value. So this is somehow deviating kt with the value of kt in this direction. And this is C in the current configuration. Let's go for D. So D has 0, 1, 0. This is the coordinate of D. This is x1, x2, and x3. This is the initial coordinate, or initial, sorry, configuration. So we put it into the star equation, and we have, let's say, so only x2 is 1. So 0 E1 plus 1 plus kt E2 plus 0 E3. So as you see, assuming k is larger than 0, we see that this point is also changing, is also moving in the right direction, but its x coordinate, it does not change. All right, so we have it here. So this is changing with kt, and it is changing in this direction. This is what we call the current configuration, which I guess that I made a mistake here. We have 0 here, E1, and this kt is for this one, not for this one. It's 1 plus, this is 0 plus kt E1, if I'm not mistaken. So this is 0, 1, 0, true, and this is kt. Great. Now it becomes kt E1 plus 1 E2 plus 0 E3. So we have the same x2, but E1 or x1 is just moved in this direction, in the right, to the right by the value of kt. So now you understand why we use the kinematic of continuum for this module, or for this chapter, why the book used this title, because this is the motion. This is the kinematic of the particles. This is how the particle move to characterize or to explain, to mention the configuration, the current and reference configuration. So next we have the Eulerian and Lagrangian point of view. Eulerian. You may heard of Eulerian point of view in fluid mechanics, but let's somehow elaborate on these two terms in here. So for the Lagrangian, suppose you have a particle like this. So you have a configuration like this, you have a continuum like this, and you have a particle right over here. So if you move with this particle, this is the base configuration, or maybe it's better to write reference. So if you move with this particle here, this is T0, to the current configuration, a time t, and this is how it deformed. So you move with this particle. So we call it Lagrangian point of view. So it is not important what kind of quantity you have, whether it is displacement, velocity, stress, strain, work, power, energy, temperature, or whatever. You move with your with your particle, and you trace it at each time until you reach the time at when you want to measure that that parameter once more. So we call this a Lagrangian point of view. And the book used actually the, let's say, hat here. So it says that if you have a parameter like theta, which is the temperature, is indication for temperature, you have theta hat x1, x2, x3, and t. So it is a function of its location of its position at time t. This is usually, not always, usually used in solid mechanics, where you have, you have, for example, a kind of beam, and you want to know how it deforms under a certain kind of load, right? So you want to know how this point here is basically changing. What is the kinematic of this particle, for example, here? This is usually used in solid mechanics. Anyway, double underline it. So usually used in solid mechanics. But if you have, let's write it like this. So if you have maybe this one. So if you have a particle like this, for example, this is your, for example, let's say configuration, and you want to know that at this time t, what is the value of, for example, velocity, temperature, energy, work, or whatever of these kind of particles which are actually crossing this boundary here. So you have a boundary like this, and you want to know that, for example, this upcoming, let's say, particle here, when it arrives here, what is its velocity? What is the value of its velocity? If it goes away, then you don't know what is its value at this point, for example, here, at this time, for example, if this is t, this is t plus delta t. You don't know it. You only know the value of t. If you want to know what is the value of, what is its value at t plus delta t, then you have to measure it again. This is mostly used in solid mechanics, where you have a flow, for example, and, for example, it has a velocity, and you want to know what is the velocity of the fluid at this intersection, or at this time here. So you will see the velocity of the particles which are crossing this, let's say, boundary or this cross section at time equal to t. So here you do not necessarily trace your, let's say, particle. So you do not move it. You are sitting here, for example, you're sitting here. You do not know what is their value of your particle here, here, here. But as soon as it goes here, it crosses the line that you, the time that you actually specified, then you will be able to know what is the value of, for example, velocity or temperature or whatever. If it crosses that, then you don't know what it is. All right. So here, the book used theta, for example, for the temperature with tilde. And then we have a small x1, x2, x3 at time t. Here, we said that the base configuration is important. Here, the current configuration is important because we want to know that at a specific time or location, what is the value of, for example, temperature. This is usually used in fluid mechanics. But this doesn't mean that you can't use, for example, Lagrangian. I can fit all of them. Okay, you can use Lagrangian in fluid mechanics, or for example, Eulerian in solid mechanics. You can also combine them together. And they are also convertible. So you can convert Lagrangian point of view to Eulerian and vice versa. They all give you the same value, but from a different perspective, from a different point of view. Therefore, they are equivalent. And it depends on how, on which tools you pick. So if you have a problem in solid mechanics, it's better to use Lagrangian point of view. However, if you have a problem in fluid mechanics, it's better to use the Eulerian point of view. But it doesn't mean that you can't use the Lagrangian point of view in fluid mechanics. You can use it, but it is way too difficult to trace a particle. For example, suppose you have a river like this, and you want to know what is the temperature of this particle here. So you have to all trace it where it goes and read it with time for different times. This is somehow impossible. But if you, for example, define a boundary here, a cross-section here, so at time equal to, for example, T, you know that, okay, all the particles have this temperature, or the temperature gradient is like this, for example, or some other kind of, pattern. This is much easier in fluid mechanics. That's why we use the Eulerian point of view. All right. The book also uses, material coordinate or material, sorry, Lagrangian or material description. This term. Also, it uses spatial description. For the Eulerian also. So let's clarify this and let's convert this, Lagrangian to Eulerian, vice versa, through an example here. So we have a very nice example. Example 3.21. So it says that if you have a motion x1 is equal to capital X1 plus kt x2. x2 is 1 plus kt x2, and x3 is equal to capital x3. And if you have a temperature theta equal to alpha x1 plus x2, then, okay, A. Find the material description of the temperature. And the material description, as you see here, this is the spatial description of the temperature field. So it is like, theta tilde. So if you want to find theta hat of it, so we have to convert this kind of, description into this spatial description into a material description or Lagrangian point of view. And the book actually didn't put this tilde here because it already uses small letters x1 and x2. So you know that you are in spatial coordinate or description. So this is the spatial description, and we want to know what is the material description or the Lagrange description, Lagrangian point of view here. So then theta is equal to alpha x1 plus x2. And for this, we only need to substitute x1 from here and here and x2 into here. So we have x1 plus kt x2, sorry, plus 1 plus kt x2. So it is equal to, so we have x2, x2. So we have alpha x1 plus 1 plus 2 kt x2. And this is nothing but material description, or the Lagrangian point of view of this temperature field. This is the Eulerian. All right. So part B says, obtain the velocity. So if we wanted to find the velocity, we have to use the, let's say, the Lagrangian point of view. Why? Because in Eulerian point of view, if you remember, if this is your eye and you're looking at this, this time or this cross section at t, so you see that you only can have the value here, for example, the value of temperature at this time t here. So after a time delta t, so this is t plus delta t, so you don't have the value. So it is somehow, pointless, meaningless to say that, okay, you have the velocity here, the change in velocity, equal to something in Eulerian point of view. So that's why we use the Lagrangian point of view, and we write v is equal to, since v is, let's say, a vector, so we use vi is partial derivative of xi with respect to t in the reference configuration where the book used xi fixed. So here you have xi as a function of capital Xj and t. So you have the let's say the initial configuration or coordinate and time t. So if we do this, so we have v1 is basically equal to, so if we take this derivative with respect to time, so we have kx2, v2 is kx2 again, and v3 is basically 0. Therefore, we have v as kx2 e1 plus kx2 e2 plus 0 e3. So I just don't write it. So now this is your v, as you see here, your velocity in in material description. But if you can calculate x2 and you substitute for capital X2, if you replace capital X2 with small x2, you'll be able to write for the you'll be able to find v actually in or the velocity in spatial description. So to get v in a spatial coordinate, we replace, or it's better to say we find x2 in terms of small x, i's, for example, x1, x2, x3, I don't know, we have to find it. And then substitute it with x2 in, let's say, double star. So from here, we have x2. We can calculate it from here. So it is x2, 1 kt. So 1 plus kt, capital X. Therefore, small x is x2, or let's say 1 divided by 1 plus kt x2. Perfect. And now we replace, so v in the spatial coordinate is k, and instead of this x here, x2, we write this. So it is basically k divided by 1 plus kt x2 e1 plus, then we have k times x2, which is 1 plus kt x2 e2. Great. Then this is the velocity in, let's say, a spatial description. Great. So you saw that before this, we were not able to calculate this velocity in spatial description, because it was somehow pointless, as I already mentioned, because we were not able to see this change in time. So the change of displacement or distance with respect to time. Therefore, we solved, or we derived the expression in the material description, and then from material description we used to derive the velocity in a spatial description. All right, so next we have the material derivative. So you already saw here that we can convert the material description to spatial description, and here vice versa. So we had the material description, and from here we calculated the spatial description. So basically these 2 points of view, Eulerian and Lagrangian, they are the same. So they give same result. So for example, if velocity in one point of view is 0, it will be 0 in another point of view. Therefore, they are equivalent. And here we are using material derivative just to say that we want to extract, we want to get a kind of equation or relation where we will be able to calculate the derivative from the spatial description, as well as as the one that we had for the material description. So in material description, it was quite easy because we had the derivative of our coordinates with respect to time, but here in spatial description, it was not that easy and straightforward. So we're going to establish a kind of relation where we will be able to calculate these derivatives with respect to the spatial description. All right. So for this, we already said that we use the material derivative here. So if you have this kind of scalar field, or for example a vector field, this expression for the spatial description will be different. Therefore, we first consider a scalar quantity. So right here, for a scalar field. So for a scalar field, what do we have is something like, let's say, theta, the temperature. It is a function of x1, x2, x3, and t. And if you know, here we're using the Lagrangian point of view. So you can put this hat in here. So I just remove it because I want you to get used to this kind of notation that if we have capital X, so we're referring to the the initial configuration, and we are actually referring to the base configuration. All right. So if you want to take the derivative, so and this material derivative is defined as this. So this is the material derivative. So if you want to calculate d theta with respect to t, then we get partial derivative of theta, which is here. So it is x1, x2, x3, and t with respect to t, where xi is fixed. So we are in the current configuration. But what if we have, this is for the material description, but what if we are in the spatial description? So for this one, let me just change the color maybe. So if we are in the spatial direction, in the spatial description, so we have theta at theta small x, x2, x1, x2, and x3, and t, and we can put a tilde here, but I'm going to remove this. So we know that theta is a function of x2, and x3. So we are in a spatial coordinate. So if we want to calculate this d theta with respect to t, which is basically this one, so I have d theta x1, x2, x3, and then t with respect to t. So I can use the chain rule because I know theta is a function of x and x is a function of t. So I have partial derivative of this theta with respect to x1 times partial derivative of x1 with respect to t. This is the chain rule. Plus, I know theta is, again, a function of x2, where x2 is a function of t, plus partial derivative of theta with respect to x3. I know x3 is also a function of t time. So partial derivative of x3 with respect to t. Plus, I have also another one, because I know theta is a function of x1, x2, x3, and also t. Let me just write this as capital. So I have partial derivative of theta with respect to t. Therefore, you can get that this is nothing but v1. This is v2. Sorry. This is v3. Therefore, we have, I write this, partial derivative of theta with respect to t, plus partial derivative of theta with respect to x1, v1 plus partial derivative of theta with respect to x2, v2 plus partial derivative of theta with respect to x3, v3. So now I can write d theta, or maybe I can write it here. So I can write that this is the partial derivative of theta with respect to t plus this is nothing but v1, v2, v3, or vi, and this is 1, 2, 3. So I sum over the dummy index. So I have vi partial derivative of theta with respect to xi. So I get this, and this is nothing but d theta dt. Or I can write this in, this is the, let's say, initial notation. In tensorial notation, I have d theta dt, partial derivative, d theta dt is equal to, this is partial derivative of theta with respect to t plus this is vi, and this is nothing but the gradient. So you have the partial derivative of theta with respect to xi. This is the gradient of theta, this scalar field, which is basically let's say kind of vector. So here you see that we have a scalar value here, so we put a dot in here. So vi dot this is the gradient del v here. So as you see here, we have the material derivative d theta dt equal to partial derivative of the scalar field in, and let's say in the spatial coordinate, plus vi, the velocity, dot the dot product with the gradient. This is a vector, this is a vector, and this dot gives a scalar. This is also scalar. So this is material, this is in the spatial description. And of course in tensorial, sorry, this is V, tensorial notation. This is again spatial description. And let's say indicial notation. And if you, for example, if you want to use this, in spherical or cylindrical coordinate system, you have to use this tensorial notation, because you know the gradient of this is theta. The gradient of theta, which is a vector, so the gradient of theta in coordinates in Cartesian coordinate system is this, but in, for example, a spherical or polar or cylindrical coordinate system, it is different. So this is the complete form or relation. So you have V, and you can calculate their, let's say their dot product, and then you calculate the material derivative. For example, if you recall, in cylindrical coordinate system, or maybe del theta, which was the gradient of scalar field like theta it was partial derivative of theta with respect to r, er, plus, because we know that gradient will increase the order. So if we have a scalar, then you get a vector, plus 1 over r partial derivative of theta with respect to theta, and this is basically capital theta, e theta plus partial derivative of theta with respect to z, ez. So don't confuse this theta with this theta. This is temperature, and this is, the cylindrical coordinate. So if you have this, so then you will be able to easily calculate d theta dt equal to partial derivative of theta with respect to t plus this expression here. So then you have v, which is v r e r, plus v theta e theta plus v z e z dot this in here. So if I copy, paste here. So you get partial derivative of theta with respect to t plus, so it becomes vr partial derivative of theta with respect to r plus v theta divided by r partial derivative of theta with respect to theta plus vz partial derivative of theta with respect to z. All right. So now, what if you have a vector field? So we already discussed what it is for a scalar field. But what if we have a vector field for a vector field? And the book actually brought this with the concept of acceleration of a particle. So it said that if you have v, which is the velocity in this, for example, in the, let's say, in the material description, you have the partial derivative of x with respect to t, where capital X is fixed, then you say that this is dx dt, right? But if you have something like acceleration, so it is the partial derivative of v with respect to t, where xi is fixed, and this is capital X. Basically, this is equal to dv dt, where this v, as you see here, is vector. So you want to know what is this vector. All right, we follow the same, before doing that, this is the material description. So if you have, equate the motion in the material description, you easily take the derivative of that vector field. For example, here, velocity with respect to t, and then you have it right there. So you have the acceleration. But what if you want to what if you want to get dv dt, where v is of course a vector, in spatial coordinate? So in the spatial coordinate, you know that v basically is v1 e1 plus v2 e2 plus v3 e3. You know that all of these are, this is a vector, right? And v1 is of course a function of x, of its position and time. And also each vi is a function of, for example, xj and time t. Therefore, v is basically v1, x1, x2, x3, t, e1 plus v2 is a function of x1, x2, x3, t, e2 plus v3 is a function of x1, x2, x3, t, e3, like the one that we had in here. So theta was a function of x, position, and time. So each v component is also a function of x and t. So if you want to calculate a, for example, this is dv dt. So you have to use, again, the chain rule. So you have you have partial derivative of v1 with respect to x1 times partial derivative of x1 with respect to t plus, you know that again v1 is a function of x2 times x2 partial derivative of t plus partial derivative of v1 with respect to x3 partial derivative of x3 with respect to t plus, you know that v1 is a function of t, so v1 with respect to t plus partial derivative of v2 is a function of x1 partial derivative of x1 with respect to t plus partial derivative of v2 with respect to x2 times x2 with respect to t plus partial derivative of, again, v2 because it is a function of x3 times x partial derivative of x3 with respect to t plus partial derivative of v2 with respect to t plus partial derivative of v3 with respect to x1 times partial derivative of x1 with respect to t plus partial derivative of v3 with respect to x2 times partial derivative of x2 with respect to t plus partial derivative of v3 with respect to x3 times x3 partial derivative of x3 with respect to t plus partial derivative of v3 with respect to t. So if I reorganize, so you'll see that we have here partial derivative of v I with respect to t, so I can be 1, 2, 3, plus here you can see that I have this, for example, as this is v1, you see here, this is v2, this is v3, and we go for the rest. So we have v 1, 2, 3 partial derivative of v with respect to x, and if you see here, these two indices are the same, so vj, j, because I'm going to have I in here, so this is I, so j is the dummy index, and what I get here is basically ai, so I get a vector. So you see that the material derivative of a vector field in a spatial coordinate system, in a spatial description, is a vector. So if if I just draw rectangular here, right? So spatial description, and of course in index notation or in indicial notation, and of course in Cartesian coordinate system. So if I bring it into, its general form, I have a equal to partial derivative of v with respect to t plus, what is this? This is the partial derivative of vi with respect to xj, and nothing but the gradient of a vector field. So here I have the gradient of a vector field times this vector here. That's it. So in general, I get something like this. This is the spatial description in tensorial notation. So basically, it means that if you have for example, the cylindrical coordinate system, for example, so in cylindrical coordinate system, you know that del v is basically a tensor. So you get something like this. I'm not going to write them. And v is basically nothing but vr, v theta, and vz in cylindrical coordinate system. So finally, you get a vector, right? And this is also a vector. So vector plus a vector gives you a vector. All right, so just to recap, if you look at this equation here, let me just copy and paste this in here. Let's say that overall, or maybe therefore, in general, for a vector, for a scalar field, for a scalar field, we have this equation here. So if I just paste it in here, so you get something like this. So if I substitute this with, for example, a black square here, so for a scalar field, if you have this, so you get this. So if you have a scalar field and you want to calculate in general for the spatial, let's say, description, of course. So if you have a scalar field, the derivative of it, or the the derivative of it with respect to time, is the partial derivative of that scalar field with respect to time plus the dot product of velocity and the gradient of that scalar field. So for a vector field, if you have a vector field, let's call it this black, let's say, triangle. So you have something like this. So so if I just copy this and paste it here, so you have this. So I can remove this in here and also this in here. And instead of writing this A, maybe I write d dt of, sorry, and this is, of course, a triangle, a black triangle. So if you have a vector field, so the derivative of it with respect to time, it is equal to the partial derivative of that vector field with time plus this gradient, the gradient of that vector field, which is, of course, as we already mentioned, the gradient increases the order of a tensor field by 1. So if you have a vector field, you get a tensor. So this is a tensor, and the product of a tensor of the, let's say, the gradient and the velocity. All right. All right, so there is a very nice example here, which I think will shed light on the difference between the Eulerian and Lagrangian point of views, and shows that they are they actually imply the same concept or result. So we have example 3.24 in here. So if you look here, we have a velocity field. So it is, the problem is giving us a velocity field where v1 is equal to kx1 divided by 1 plus kt. v2 is basically kx2 divided by 1 plus kt. And v3 is equal to kx3 divided by 1 plus kt. And in the first place, in part A, we're going to find the acceleration field. So as you see here, everything is in, let's say, in the spatial coordinate. So I can write this, A1, for example. It's we already had it from here. So if you have a vector field, so A, or the acceleration, for example, or let's say dv dt is equal to this A in here, which is equal to the the partial derivative of that scalar with respect to time, where here it is, for example, for this one. So let's say we have A, and this is minus. So if this is the partial derivative of v1 e1 plus v2 e2 plus v3 e3 plus the gradient of v times v, right? All right. So v1 is equal to, the partial derivative of v1 with respect to t, I am calculating the first one. It is basically minus k squared divided by 1 plus kt x1. And then I have partial derivative of v2 with respect to t, which is the same because we have the same expressions for v1, v2, and v3. They only differ for x1, x2, and x3. So we have partial derivative of v3 with respect to t is equal to minus k squared divided by 1 plus kt x3. So we calculate this part in here, and we have del v. All right. So del v in here is equal to, if you remember, so it was partial derivative of v1 with respect to x1, then partial derivative of v1 with respect to x2, partial derivative of v1 with respect to x3, and then we went down for the rest. So it is basically equal to, so the partial derivative of v1 with respect to x1 is k divided by 1 plus kt. So it is k divided by 1 plus kt. So since it was x1 here, so these two are 0, this is 0. K 1 plus kt, this is 0, 0, 0, k divided by 1 kt. So if you can't recall this, so I refer you to the relevant videos in module 1. So we have this one, and then we have v, which is here. So if I write a is equal to this in here, so minus k divided by 1 plus kt x1 e1 plus, minus k, this is squared, divided by 1 plus kt x2 e2 plus, this is x2 e2, and so I have minus k squared divided by 1 plus kt x3 e3. All right, so now I have this part. So I have del v, the product of del v and v. So I have v. If I put v here, so I have, this is my v1, v2, and v3. So if I times them with this, so I get a vector like k squared 1 plus kt x1 e1 plus k squared divided by 1 plus kt x2 e2 plus k squared divided by 1 plus kt x3 e3. So if you see here, you can just cancel out all these terms together. So finally you get 0. This is somehow weird, because we saw here that our velocity is changing with time. Yes, it is changing with time, but it is changing in a spatial description. Therefore, you will get, for example, at time t equal to 0, for example, all these values represent a constant value of velocity. If t is equal to 2, then, for example, for the value of k equal to 1, then this gives x1 divided by 1 plus k2. And here is x2 divided by 1 plus, sorry, this is 2. And this is also equal to x3 divided by 1 plus 2. And x1, x2, and x3, they are, for example, 1, 1, and this is 2, for example. So if you see here, they all give one value, one constant value. This is 2 divided by 3. This is equal to 1 divided by 3. This is 1 divided by 3. So if we change t, 2 for k is 1, still is 1, and t2 to 4, for example, we have 4 in here, 4 in here, and then we have 4 in here. So this becomes 5, this is 5, and this becomes 5. Therefore, you see that all of them gives a constant value for v. Therefore, for a constant value, we have 0 acceleration. We know that v is the derivative, a is the derivative of velocity with respect to time. So if you have a constant value, you get 0 acceleration. You can also recall this from your courses in dynamics. All right. So now you see that the Lagrangian actually gives you the same, the same expectation that you have from Lagrangian. All right. So the second part basically says find the path. So here, if I find the path, the initial path, for example, so if I find, for example, x as a function of xi's as a function of xj and t, then I will be able to calculate v with respect to t in xi fixed. The material derivative in the material description. Therefore, I can also show that that the value of, let's say, velocity is constant, and also this gives 0 acceleration. So let's do this. So for this one, we know that vi, or v of each, let's say v of each component, v1, v2, and v3, it is the partial derivative of xi with respect to t at xi fixed. This is true. This is something that we already mentioned. And it is nothing but k x1, x2, x3 divided by 1 plus kt. It's because, all their values, they have the same, let's say, they have the same, coefficients for v. Or maybe it would be better to write it as v1 is, so if you want to find v1, it is equal to partial derivative of x1 with respect to x3 when x1 is fixed. So here I have x1. So you can also do this for v2 and v3 and find the relevant relations. So if you have this, then you have to integrate to get the displacement. We integrate, right? All right. So we have the partial derivative of xi. So with respect to t is equal to k, and this is 1, of course, kx1, 1 plus kt. And remember here that since x1 is just x1, so it is only dependent on t. So we change this partial to d. Here we had this I in here. So we had a partial derivative of xi with respect to t. So I put a partial. But here x1 is only a function of t. So it changed only with t. So I integrate, so I do some manipulation. So I put this x1 here, I keep k in here, 1 plus kt in here, and I have dt. So if I integrate, for example, here from our initial to our, for example, final configuration, and say that t, the initial time is 0 and the the current configuration occurs at time t. So I have ln of x1, because this is ln, x1 minus ln x1 is equal to k divided by, so if this is k, so this becomes 1 over k, so it is ln of 1 plus kt plus, because t sits here, so it is t, sorry, minus ln 1 plus k times 0. So this is basically 0, 1 plus 0 is 1, ln 1 is 0. So I have here, and I can write this as ln of x1, x divided by x1, ln plus kt, and finally I can write x1 is equal to 1 plus kt x2, oh sorry, x1. So by following similar procedures, so x2 is equal to 1 plus kt x2, and x3 is equal to 1 plus kt x3. So now you see here we have x1, x2, and x3. So v is nothing but partial derivative of xi, vi, with respect to t. So it is equal to kt, sorry, it is equal to k x1 e1 plus k x2 e2, and then k x3 e3. So you see here that all these refer to a constant value for v1, v2, and v3, similar to what we already had in the spatial description. So that's why if we take the derivative of this, so we say that vi with respect to t, this is xi fixed, this is xi fixed, this will be 0 e1 plus 0 e2 plus 0 e3. So you see that here we get the same result as, 0E1 plus 0E2 plus 0E3 in here, as we had in spatial description. So they are equivalent and they give the same result.